we're looking at the difference between precision and accuracy. And while those words are often used interchangeably, actually they mean something totally different. And so when I finish with this lesson today, it's going to be really important, and you will be able to understand what the difference between precision is versus accuracy. To kind of get us started, I want to watch a quick video that kind of does a really nice job of explaining.
As the story goes, the legendary marksman William Tell was forced into a cruel challenge by a corrupt lord. William's son was to be executed unless William could shoot an apple off his head. William succeeded, but let's imagine two variations on the tale. In the first variation, the Lord hires a bandit to steal William's trusty crossbow, so he is forced to borrow an inferior one from a peasant. However, the borrowed crossbow isn't adjusted perfectly, and William finds that his practice shots cluster in a tight spread beneath the bullseye. Fortunately, he has time to correct for it before it's too late. Variation 2. William begins to doubt his skills in the long hours before the challenge, and his hand develops a tremor. His practice shots still cluster around the apple, but in a random pattern. Occasionally, he hits the apple, but with the wobble, there is no guarantee of a bullseye. He must settle his nervous hand and restore the certainty in his aim to save his son. At the heart of these variations are two terms often used interchangeably: accuracy and precision. The distinction between the two is actually critical for many scientific endeavors. Accuracy involves how close you come to the correct result. Your accuracy improves with tools that are calibrated correctly and that you're well trained on. Precision, on the other hand, is how consistently you can get that result using the same method. Your precision improves with more finely incremented tools that require less estimation. The story of the stolen crossbow was one of precision without accuracy. William got the same wrong result each time he fired. The variation with the shaky hand was one of accuracy without precision. William's bolts clustered around the correct result, but without certainty of a bullseye for any given shot. You can probably get away with low accuracy or low precision in everyday tasks, but engineers and researchers often require accuracy on microscopic levels with a high certainty of being right every time. Factories and labs increase precision through better equipment and more detailed procedures. These improvements can be expensive, so managers must decide what the acceptable uncertainty for each project is. However, investments in precision can take us beyond what was previously possible, even as far as Mars. It may surprise you that NASA does not know exactly where their probes are going to touch down on another planet. Predicting where they will land requires extensive calculations fed by measurements that don't always have a precise answer. How does the Martian atmosphere's density change at different elevations? What angle will the probe hit the atmosphere at? What will be the speed of the probe upon entry? Computer simulators run thousands of different landing scenarios, mixing and matching values for all of the variables. Weighing all the possibilities, the computer spits out the potential area of impact in the form of a landing ellipse. In 1976, the landing ellipse for the Mars Viking lander was 62 by 174 miles, nearly the area of New Jersey. With such a limitation, NASA had to ignore many interesting but risky landing areas. Since then, new information about the Martian atmosphere, improved spacecraft technology, and more powerful computer simulations have drastically reduced uncertainty. In 2012, the landing ellipse for the Curiosity lander was only 4 miles wide by 12 miles long, an area more than 200 times smaller than Viking's. This allowed NASA to target a specific spot in Gale Crater, a previously unlandable area of high scientific interest. While we ultimately strive for accuracy, precision reflects our certainty of reliably achieving it. With these two principles in mind, we can shoot for the stars and be confident of hitting them every time.
Let me give you a couple of definitions, please, to copy down in your notes. It's really just two. First of all, precision is the level of detail a measurement determined, and it's determined by the smallest unit. So it's a level of detail of a measurement, and it's determined by the smallest unit. That's precision. In contrast to that, accuracy. Now, accuracy is the closeness of a given measurement or value to the actual measurement. Generally speaking, the smaller the unit that we're measuring in is more precise than a larger unit. But accuracy is actually getting the value we're supposed to. Okay? So the next slide is found in your notes. Looks like this, and I've got a printed copy here that I'm going to actually work off of. If you want to in your notes, you can just jot down 3 columns, or 4 columns, I should say. That's fine. What we're going to do is we've got some measurements. We want to talk about which unit is more precise. So looking at the first measurement taken, I've got 4 grams, and I've got a second measurement of 4.3 grams. We want to think about what is the smallest unit in that measurement. These are whole grams. There are no decimal portions, but in the second measurement, we see that there is 1/10 of a gram right there. In fact, it's 4 3/10 of a gram. So my smaller unit there is 1/10 of a gram. And since this contains tenths of a gram and this one does not, the more precise measurement is 4.3 grams. Remember, it's not the smallest number, but rather the smallest unit. Check out the next one. Next one is, the first measurement was 5 71/100ths of an ounce. My smallest unit is the hundredths of an ounce versus 5 7/10ths of an ounce. So my smaller unit there is 1/100th of an ounce, meaning that the more precise measurement is 5.71 ounces. So far, that seems pretty straightforward as you're writing that down. Now I get to the third one, a little difference here. Because notice that this is 4 2/10 meters. What's the unit on measurement 2? Do you know? it's 422, what's the unit here? Centimeters. Now, even though 422 looks larger than 4.2, our units are not the same. It takes 100 centimeters to equal a single meter. So centimeters are the smaller unit by far. So that means when I'm looking at trying to determine the most precise measurement between 4.2 and 422, the most precise is 422 centimeters because I'm measuring with a lot smaller unit there. A meter is about a yardstick. It's a little longer than a yardstick. Centimeter is less than an inch. See how that's a much smaller unit. It brings us to the last one. The first measurement was 7 feet 2 inches. The second measurement was 7 2/10 inch. Well, they both contain inches. Inch is the smallest unit, but 7 2/10 inches actually is measuring in tenths of an inch, which means the smallest unit here is a tenth of an inch. So the most precise measurement is 7.2 inches. Again, when we're trying to figure what is our most precise measurement, we're looking for the smallest unit. Now, how does that contrast with accuracy? Let's talk about that. Look at another example. Suppose that we have 3 scales. Each scale comes up with a little different measurement and a little different precision. Eric, he's a lab technician, and every day he needs to test those scales to make sure that they're accurate. So the way he's going to do it is he's going to take a mass or just a little weight, and he knows that that weight weighs exactly 8.000 grams. That weight weighs that amount, never changes because it's an actual weight. Here it is. He's going to set that weight on each scale. And when he does, he's going to check and see, okay, what is the measurement for this and how accurate is it, how far is it off? Now, just based on what we've talked about, let's first talk about precision. Scale 1 measures to 1/100th of a gram. So we have 8.02, so it's 8 2/100ths. Scale 2 measures to 1/10th of a gram. And scale 3 measures to 1,000th of a gram. So which scale is the most accurate using the smallest unit? Is it scale 1 with hundredths of a gram? Is it scale 2 with tenths of a gram? Or scale 3 with thousandths of a gram? Somebody want to answer that either online or in person? Which scale would then be the most precise? I'll wait on you. What do you think? Yep. Somebody said in the classroom, the measurement for scale 3 is the most precise, because it measures to the nearest thousandth of an inch. No, excuse me, thousandth of a gram. Not inches, that's distance. Grams. And that's the smaller of the units. That's the smallest unit. So that makes scale 3 the most precise. But we really want to talk about what is the most accurate. Well, in order to figure out accuracy, we're going to take the actual measure. Now, we know that this weight was 8.000 grams, exactly 8 grams. And we want to see what is the difference. So if we figure out what the difference is, we're going to have to subtract what the measurement is with the scale. So to find the accuracy of each of these, we're going to find that difference and then take its absolute value, and we'll talk about what that means. Well, scale 1 measured, it came in a measurement of 8.02. So if I'm going to figure out what my actual measurement is, or the accuracy of it is, I'll take the 8 grams and subtract from it 8.02, just like that. When I subtract it, I get a negative 2/100ths. Now, remember, you probably maybe recall from middle school that these marks mean absolute value. We just want to know the absolute value of that number. It literally means distance from 0, but for us here, what it really means is we're not going to really think about the negative side. We're just going to write down the value we get. So the accuracy, first one comes in at 0.02. The scale number 2, when he weighed it, it gave a measurement of 7.9. So we're going to do the same thing here. We're going to take the 8, subtract from it 7.9. When we do that, now I could put in 8.0000, but I'm just going to put 8. It'll give me the answer I need. I get 0.1. When we weighed the weight on the third scale, we got 8.029 grams. So back here, we'll take 8 and subtract from it 8.029. And we'll get 0.029. Now, notice I got a negative, but again, absolute value, not going to worry about that. Here's what I need to do. I need to determine which of these measurements of accuracy, is the smallest, because the smallest one of those is the most accurate, because it's the closest to the target that we're looking for. You may remember from middle school when I go to compare decimals, I take it decimal place by decimal place. Well, if I look at the tenths place first, I have a 0, a 1, and a 0. Well, 1 is larger than 0. So I know that 0.1 is the largest of the 3. So I'm going to rank them from smallest to largest. That ranks 3. So I move over a decimal place. Now I'm comparing 2 to 2. I don't have to worry about this one because I've already know it's the largest one. 2 and 2 are equal, aren't they? So far, based on the hundredths place, they're still equal. I'm going to put a 0 here because if it's not there, that's what is actually there. Compare 0 to 9. Which is bigger, 0 or 9? 9 is larger, isn't it? So if 9 is larger here, I know this is larger than the first one. So my second largest is 0.29, and my smallest one is this. If I wrote those in order from least to greatest, I would write 0.02 is less than 0.029, which is less than 0.1. So that's an order from smallest to largest. Here's what I can conclude from that. Based on that, the measurement for scale 1, because it has the smallest accuracy, it's the closest to the target, which is 0.2 grams. It measures in at 8.21 grams, and it's 0.02 grams from the actual amount. It's the most accurate because it is the closest to the target. It's the smallest difference because it is less than the third one, which is also less than the second one. So I know the most accurate one is the first scale. Remember, earlier we said that the most precise one was the third scale. It is still the most precise, but it doesn't measure accurately. It just measures in smaller units. So that's the difference between accuracy and precision.